Okay, so now we're going to start looking at some other measurements, some numerical measures for our data sets. And the first thing we're going to be looking at is measures of center. So the big ones we're going to be doing is mean, median, and mode. You can see my little comic right here talking about mean, median, and mode. I put this on here because of this. Isn't mean just a fancy name for average? Median and clairvoyant, that's medium, but that's okay. This is the joke part. So first, I want to talk about a little bit about notation, and this is one of the things that people sometimes have a little bit of trouble with, so I want to talk about this first. So if you take a sample of n observations, and we can denote that by x sub 1, so this just is a sub 1, sub 2, and this is just denoting different observations. So this might be like, first observation might be 4.5, the second one might be 5.4, the third one might be 2.3. They don't have to be in order, ... and the last one is 3.6, something like that. So this is just telling me this is x1, x2, x3, this could be x4. So if I have 4 observations, that's what they would be. And what that allows us to do is use this summation. This is the Greek letter sigma, and this is actually a capital sigma because we'll be using the lowercase sigma here in a little bit. And it means sum. So this means sum up. This right here means sum up all the x sub i's for I equals 1 to n. Or we can leave that off. If it's 1 and n, we can just leave that off, and that just means just add up all the observations. So that would just be all of these numbers added together. So that's exactly what we would do. So if in this case, if I wanted the sum I equals 1 to 4 of x sub I would just go 4.5 plus 5.4 plus 2.3 plus 3.6, which, let's see, that's 9.9 plus 5.9, so 15.8. And so you could easily find the sum of these 4 numbers. Okay. So this brings me to my first definition, which is the mean of a data set. Now, like we said in the beginning, that joke, is just a fancy word for the average. Okay? Is mean any fancier than average? Average is a little fancier. So for the case of our 4 numbers we had before, we're going to take this sum, which we said 15.8, and we're going to divide that by 4. And let's see, that's going to be, 15.8 divided by 4 is 3.95. So we have a 3.95 average of those 4 numbers that I had in the previous page. So let's look at the median of a data set. Now, to find the median, the data does have to be arranged in increasing order. So looking at the data set that we were just looking at, I had 4.5, 5.4, 2.3, and 3.6. So in order to look at the median, I actually have to reorder this into increasing order like that. Now, if the number of observations is odd, the median is in the middle. But in this case, we have 4 observations, so it's even. So the middle would be here, and there's no number here. What would we choose? So, but if the number of observations is even, so ours is 4, then the median is the mean of the 2 middle observations. So in this case, we don't have 2 medians. We don't say it's these 2. We take the average of just these 2 numbers. So we take the average of 3.6 and 4.5. And if we do this, let's see, 3.6 plus 4.5 divided by 2 is, now if I go to my calculator, I want you to show you something. You have to be very, very careful. If I type this in, just like this, then the problem with the calculator is going to read this as 4.5 divided by 2 because your calculator is going to do order of operations. We don't want that. We want this to be added first. So we're going to go back here and we're going to say no. We want this in parentheses. So you have parentheses here. And to insert something, you can hit second delete, which allows you to insert. So we insert parenthesis there. And I'm going to insert a close parenthesis, second delete to insert a close parenthesis there. Now that it'll do that, it's going to add those numbers first. And it's 4.05. So as you can see, the mean and the median are fairly close in this one. It was 3.95 and 4.05. So that they're it's very, very similar. It's around 4. So let's talk a little bit about the best measures of center. Now, one of the ways we can do that is let's think about an NBA basketball player's high school basketball team. And let's look at what those individuals do now. So let's say that team has a person who's now a janitor. They make $13 an hour. So X1 is 13. X2, a delivery truck driver, he makes 14. A retail store assistant manager, he makes 18 an hour. An automobile mechanic makes about 20. The firefighter makes 24. The nurse makes 25. The department store buyer, 28. An automobile salesman, 32 with commissions, but we'll just say that. IT project manager, 41. But the NBA basketball player's salary is $20 million a year, which comes out to about $10,000. Now, let's take the mean hourly salary without this outlying observation, this very different observation than the rest of them. And if we were going to do that, we can go over here and we can simply add the numbers up. Oops, my plus didn't get there. Plus 14, plus 18, plus 20, plus 24, plus 25, plus 28, plus 32, plus 41. Now I'm going to hit enter and let that get that. Then I will divide that by 9. Okay, without his salary, without counting the NBA player, it's $23.89. So I want you to be careful too when you're rounding. So we see that this 8, the next number is more than 5, so this becomes $23.89. So what does the mean with him? Okay, let's go back to our calculator. Let's take our 215 that we had, that's the sum of the first 9, plus the $10,000 that he makes. Now let's divide that by 10. That's 1,021. So that's 1,021.50. Okay. So look what happens to the mean. This one person takes the mean from $23.89 to over $1,000. Do you honestly think this is showing the center of the data in this case? You should be thinking no, because the mean hourly salary without him is only $23.89. So this doesn't make much sense. So let's look at medians. Let's go with and without him. So let's first of all look at without him. So without, what's the median? Now without him, here is the data. And we are looking at the middle number. So, and everything is in increasing order here. So 1, 2, 3, 4, 1, 2, 3, 4. The one in the middle is 24. So without him, it's $24 an hour, about the same as the mean without him. So there would be no problem there. But with him, it's going to be, so now we have, instead, now we have 10 observations. So now we want to look at the 24 and 25, and what's the average of 24 and 25? It's 24.5. So with him, it's 24.5. So the median salary is $24.50, even with the NBA player. So in this particular instance, what is the best measure of center? You want to look at the median, because this NBA player is an outlier. It's pulling this mean way up. Most of the people who are on that basketball team don't make $1,000 an hour. So really, your center of your data is more about $24.50. And with the NBA player making way more money. Okay. So let's talk next about the mode. The mode is looking at the highest frequency of a value. So if you have repeating values, so in the example that I did before with the 4 numbers, we didn't have a mode. Everything only occurred once. So it had no mode. So if a no value occurs more than once, or they all occur the same number of times, so even if I have the same thing, 3, 3, 4, 4, 5, 5, this still has no mode, because these all only occur twice. So any value that occurs with the greatest frequency is the mode of a data set. Now, it's really interesting because data can have 1, 2 modes, 3 modes, as many modes as it needs to have. For example, if this just said, if this had a 6 here, now everything isn't the same. So now this has 3 modes, 3, 4, and 5, because this occurs more than this 6. So now this data has 3 modes. So let's look at this example. So I like to think these might be some kind of grade point averages. So I just looked at the mean, median, mode of each data set. For the mean, we just added these up and divided by 5 for each of these. Here I added these up and divided by 12. So here's our means and our medians. So here, this is higher, both mean and the median. And it looks like on both data sets, our mean is just a little higher than our median. So, but what is our mode? In data set 1, we have no mode because nothing appears more than one time. But in data set 2, our mode is 4.0. So can you really call mode a measure of center? Well, maybe not. Because in this case, it's definitely not a measure of the center of the data. Because this is on the end. This is on the highest end of the data. So this is definitely not in the center of the data, is where the mode is. But it kind of gives you an idea of what is happening the most often. So let's do some of these examples. So let's look at 5, 6, 8, 8, 9. This one has one mode, 8, because 8 occurs twice. 5, 5, 6, 8, 8, 9, well, both 5 and 8 occur twice in this example, so it has 2 modes. Now we have, okay, 5 occurs twice, but 8 occurs 3 times, which makes the mode 8. So we have one mode again. Now, 5 occurs twice, 8 occurs twice, but 9 occurs 3 times. Again, one mode, 9. So looking at this one, this is very simple to the example that I did on the previous page. The 5s, the 8s, and the 9s all occur twice. The 6 only occurs once. So we have 3 modes, 5, 8, and 9. But if we take that 6 out and have 2 5s, 2 8s, and 2 9s, we have no mode. So let's take a look at mean and median and what it does to the shape of your distribution. So if your mean is higher than your median, and it depends on how much higher it is. See, in the basketball example, we were more like this. Our median was over here, and our mean was about over here somewhere. It was crazy because this number got pulled up so high. So here we have right skewed. So when your mean is greater than your median, then you tend to skew right. It means that there's one or two outlying observations over here that's pulling your mean up, but it doesn't have as much of effect on the median. And then symmetric, they're about the same. The mean almost equals the median, so they're very similar. And here, this is left skewed. So this means you have some outlying observations over here that's falsely pulling the mean down and making it look like the average, well, it is the average, but making it look like the center of the data is lower than it is. So this is when the mean is less than the median. So we should be able to get an idea of what's going on as soon as we see the mean and median. We can kind of get an idea in our head of what's going on with the data. So this tends to skew left. So now let's talk a little bit about population versus sample. Now remember, your population can be very, very large, or it can be finite. We could talk about all of the people in this class, or all the people that are taking this class this semester. Versus a sample, if I took a random sample of 10 of you, that would be very different. That would be my X bar. Okay, so if I took a sample of everybody who was taking this class, and I took 10 people, and I don't know, averaged your next test score, I could take a sample and find my X bar. Or I could take everybody who took the test, and that would give me a population mean. And that's very different. So remember, X bar is for a sample. So this is if I just took some of you. Okay. And population versus sample mean. Now, when we go to a population mean, so this is if I wanted to take the actual average of everybody who takes this next test, and I can find that for smaller finite populations. Of course, for large populations, I can't find it. I can't find the average length of salmon in the Kenai River. Can't do it, okay? It would be absolutely impossible. I can't get to them all. I could take a sample of them, but I could not get to all of them. So we kind of get ridiculous. The average number of hairs on the human head. I mean, that's counting everybody's hair on everybody's head in the world, which that would be ridiculous. So sometimes you can't get your population mean. So a lot of times we're going to call this by the Greek letter mu. And you can kind of, that's how I draw it. You can draw that like this. You get used to it. If you can't do it, just write an M. It's okay. I'll know what you mean. And it is the sum of all the data. There should be a capital N up here. Divided by big N. Big N being the population size. Okay. But you, like I said, you have to have access to every data point in the population. So, and like I said, many times we look at this by frequency and multiplying each observation with how many times it appears. We're going to do that in chapter 5. You'll be seeing that. Don't worry about that right now. But just remember that the population mean, go away. The population mean is this Greek letter mu. You can remember that by it's weird in Greek, and most of the time we can't even find what it is. The sample mean is X bar. So that's the difference. And this is really, really important later on as we get into this other things in this class. So let's talk about measures of variation. So here's my joke for that. It's the new keyboard for the statistics lab. Once you learn how to use it, it will make computation of the standard deviation easier. After I'm done showing you how to find this, I'm going to actually show you how to use your calculator to find all of these things and make it very, very simple for you. But let's talk a little bit about standard deviation, what it does and what it is. It's a very abstract concept. So I want you to consider these daycare facilities for children. So let's say we have these 3 daycare facilities, and they're all very different. This one has all ages. You have a 1-year-old, you have a 7-year-old, very, very different. This one looks like it only goes from 3 to 5. Right? And so this looks like more like a preschool. This one has very different ages, has 2 infants and 2 kids that are school age, 8 years old. So we have 3 different daycares. Now, the means are equal. The means are 4, by the way. The equal medians, the medians are 4. And what is different? Now, a lot of people, when they look at this, they think, well, the modes are different. Because here, my mode is 4, here my mode is 4, but here my mode is 0 and 8. That is true. The modes are different. I could have very easily made that mode 4. But what else is different? We see that the range of ages is very different. And we're going to see that the standard deviation is very different. So, look at the oldest and youngest. And this is called the range. So here, our difference is 6 years. So my range is my max minus my min. And in this case, there's a 6-year range of children in this daycare. Here there's a 2-year range, and here there's an 8-year range. So the ranges are very different in each one of these daycares. And this actually gives you the formal definition, which I just said. Okay, so let's talk about standard deviation a minute. Now, we have this variable x, and the standard deviation of the observation, we're going to call it a sample. So we're going to say this is a sample of the kids in the daycare. It's denoted S of x, or when no confusion arises, sometimes we just say S. Your calculator calls this S of x. We'll talk about that in a minute. And you'll notice that by definition, what is S? Well, S takes each data point, subtracts its sample mean, then squares it, and then adds all those numbers up. So in the case of this first one that I had, so if we look at, let's say I look at 3 numbers. Let's just look at 3 numbers, 3, 6, and 4. Okay. Well, I don't like that. Let's do 2, 6, and 4. I'm cheating. So the average of these 3 is 4. So my x bar would be 4. And in order to find each one of these, I would go, well, this is 2 minus 4 squared, 6 minus 4 squared, 0 minus 4 squared. So here I would have 4, 4, 0. Add those numbers up, I have 8. So I want the square root of 8 over 2, square root of 4, which is 2. So my standard deviation is 2. That is my average. It's kind of a weighted average distance to the mean. Okay. So, and if I look at this, yeah, well, this is 2 away from the mean. This is 2 away from the mean. So it kind of works. The difference is a lot of times what will happen, it's kind of interesting. You notice you take a square in here and then you take the square root, but you only take the square root after you divide it, after the sum is done. So you can't skip a step and cancel the square root and the square out. You have to do it this way. You have to square each one of these first. add them up, and then divide by n minus 1, and then take your square root. And then we get it's kind of a weighted average distance to the mean of all your data points. So if you think of it that way, that's actually one of the best ways to kind of think of it logically, that it is a weighted average of difference to the mean. Okay, and here's a computational formula. This is a little simpler formula. In this case, we take each of our data points and square them. So in this case, in the previous case, this would have been 36, 16, and 4, which would be 56. And then we take the sum of the data, which would be 2, 4, and 6, which is 12, square it, divide it by 3. So 56 minus 144 over 3, and divided by 2. And then we take the square root of it. Now you'll notice we end up with the square root of 56 minus, let's see, 1493, I believe we have 48 if I'm not mistaken. And so we get the square root of 8 over 2, which is 4. Mathematically, this is exactly the same as the previous one. The reason I show you this is an easier computing formula. However, this tells us what a standard deviation is by using the definition. Okay, and I want to make sure you guys understand that these two things are not the same thing. Remember order of operations. If I take the sum of the numbers squared, that is very different than the sum of the numbers then squared. Because this means, in this case, so if I have 2, 4, and 6, this one right here means 4 plus 16 plus 36. This one means 2 plus 4 plus 6 squared. And these two things are very different. This is 56, this is 144. And these are not equal. Okay. So calculating sample standard deviation by hand. So we find the squares of each data point, then add them up. We call this the sum of squares. So in this case, so let's do a different one. Let's do the one that we had before, 4.5, 5.4, 3.6, and 2.3. So we want to find the squares of each of these numbers. So now remember the easy way to do that. I can go list, edit, and 4.5, 5.4, 3.6, 2.3. And then to square them, all I need to do is go over here, and I'm going to I make sure L2 is highlighted, and I go second 1 squared. And there's all my numbers squared. So that's the first one. And now we have to add these numbers up. Okay, now I can do that under list, math, and I want the sum. Not there. I don't want it there. Let's get out of this. Now we can go to list, math, sum of list 2. 67.66. Let's find the sum of the data. Okay, that's easy, right? Second stat, math, sum, list 1. That is 15.8. Square that sum found in step 2 and divide by n. Okay, so we need to square this, divided by 4. 62.41. subtract the answer in 3 from the answer in 1. So we have, let's go up and get it. I'm going to get it. 67.66 minus 62.41, 5.25. Divide this by n minus 1, divided by 3, 1.75. And take the square root. Square root of the second answer. Whoops. Get my second all the way in there. There we go. 1.323. Standard deviations, 3 decimal places. That's pretty good. Now, I want to show you something with your calculator. You can do something in your calculator called a 1var stat. So I can actually go here to statistics, to calc, enter. Now I have a thing that comes up here that tells me exactly list. I want list 1 because that's where my data was. Frequency list, leave it blank for now. Blank. And hit calculate. And this is what you would do if you don't get the menu. You just put L1 by second 1 right here. And look what this does for me. This gives me my X bar, which is 3.95. Gives me the sum of the data right here, which is 15.8. It gives me the sum of the squares, which was 67.66. Notice where it says SX, 1.32. That's what we found. Now this sigma we'll talk about in just a minute, n equals 4. It gives me the median, or the minimum, the first quintile, the median, the third quintile, and the maximum. We'll talk about some of those later, but you'll notice this median of 4.05, which is what we found before. Okay, let's look at this daycare example again. And you'll notice that I have all of my standard deviations for that. I'll let you look at this yourself, but you'll notice my 3 standard deviations for the 3 daycares. And you'll notice that your average distance to the mean here is 3.5 years almost. Here it's about 2 years. Here it's about 6 months. Well, that one is 2 years, but... So your weighted average difference to the mean is very different depending on, so if you were deciding on the daycare and you wanted your child to be in an environment with kids of a lot of different ages, you'd pick one of these two. If you wanted your child to be in a preschool type environment, you would pick this one. So it actually gives you much more information about it than just, say, a mean. Oh, what's your average age? Your average age is 4. Well, what's your standard deviation? Really, really important part of the... So, again, we're going to use this 1var stats. So, again, I showed you how to do it here. So, we're going to use these 2 data sets. So, you want to enter your data. So, let's stat enter, and this brings you to the edit menu. So I'm going to clear, and I'm going to go second, whoops, keep doing that, stat, whoops, there we go, stat, enter, brings us to this menu. Now remember, I have leftover things in the list, so I'm going to go up here and highlight clear, enter, go up to L2, clear, enter. Now I'm going to put this data into list 1. This first set of data, 41, 44, 45, 47, 47. Oops, my 47 didn't get in there. 48, 51, 53, 66 is the last one. Okay. Okay, I'm going to repeat this with list 2 now. Okay. 20, 37, 48. And you guys can get your calculator and follow along with what I'm doing here. And make sure you can get these same answers. Whoops. Watch for typos. It happens all the time. Okay. Why do I have more in that one? That isn't right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Uh-oh, what happened here? What did I do 2 of? Oop, I did 2. Oh, no. 20. 70, 64, 61, 53, 50, 49. 48, 48, 37, 20. Huh. Oh, what did I miss over here? 48, 51. Okay, found my typo. I had forgotten the 58 right here. Okay, so now I have both of these lists in here. Now what we're going to do is we're going to go and get each of their sample means and all the other information we want. Once your lists are entered, okay, we're going to go stat, calc, and list 1, frequency list, leave blank, cursor down, and hit calculate. Okay, so now in this case, we see our sample mean, X bar, 50. Sum of the x's, 500. Sum of the squares of the x's, 25,494. The S, so this is the standard deviation of a sample. This is the standard deviation if it were a population. We'll talk about that in a minute. N is 10. And then the arrow key, this right here, indicates that you can actually arrow down and see more information. So our minimum is 41. Our Q1 is 45. Our median is 47.5. Our Q3 is 53. Our max is 66. Together, these 5 are called the 5-number summary, because this gives you your minimum value, your first quartile, your median, your third quartile, and your maximum. So that is how you do it. Now, if I wanted to find the second one, I would simply just go stat, calc, 1 variable statistics, and change this to list 2. And I could very easily find the second one. Now, the second one still has a mean of 50, but I want you to notice what the difference is. Look at the S for the second one. So the S of X for list 2 is 14.16, much more variable. In fact, twice as variable, nearly, as this one. So the average distance to the mean, this data is not nearly as spread out as this data. So this data is more spread out, and there's more variability. So now let's look at, I promised you I would talk about population versus sample standard deviation. Now here was our definition for our sample standard deviation. Now remember, that's when we have a finite sample of a population that we either cannot get, or is too large or too inaccessible, or what have you. Now, we have to divide by that n minus 1. A lot of people get confused by that. Why are we dividing by n minus 1 and not n if it's a weighted average? And because we're using x bar to estimate the standard deviation. Now remember, x bar is an estimate all of itself. It's not the real mean. The real true population mean is some mu that we can't get to, that we don't even know. But x bar is our sample mean. So when we're taking x bar and we're using that to find the standard deviation, we have to divide by n minus 1 and not n in order to correctly estimate what we've got here. So now, if we have a population standard deviation, we could use the true mean if we know information about an entire population. So when I'm looking at your exams, your first exams, and I find the mean, I can find all of your means. So everybody who's taking this class from me this year, I'll be able to take a true population mean, and I'll be able to get a true population standard deviation as well. Then I can divide by the capital N because I'm using the distance to the true mean. Now, like I said, we have to know every single data point. We have to be able to get the true mean in order to get this. So this is denoted by the Greek letter sigma, and this is a lowercase sigma. So like I promised, we're going to use both upper and lowercase sigmas in this case. So now we have the lowercase sigma, and the easy way to remember is that we have our sample population, or sample standard deviation is S, or S of x, and our population standard deviation is this weird sigma, or sigma x. This one we don't usually know. It's weird. It's Greek to us. Okay? So here's a good picture of population versus sample. So if my population mean is mu, my standard deviation is sigma, I use a sample of it. So I find this sample. This sample mean, the mean of everything in here is x bar. The standard deviation and everything in here is S. Now, I want to tell you a couple definitions. A parameter is a descriptive measure for a population. So a parameter, mu and sigma, are parameters. A statistic are x bar and S, or S of x, doesn't matter. And we can also call these mu of x and sigma x if we have a y or whatever. If there's no confusion, we just call them mu and sigma. And so statistics are information about our sample. Parameters are information about a population. So if you hear a football statistic, the number of yards somebody's run for this season, technically that's a parameter, not a statistic, because it's using the entire population. Just one of those things. Okay, so let's talk a little bit about the quartiles. I promised I'd talk about that too. So the quartiles are like the median of the top and the bottom half of the data when it's sorted. So if I have a bunch of data, let's see, 2, 2, 3, 6, 8, 9, 15, 22, 31. 1, 2, 3, 4, 5, 6. 35, 42, 56. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, there we go. So if we look at the median is the average of 9 and 15. So let's see, that's 24. Half 24 is 12. So our median is 12. So my first quartile is going to be the median of this half of the data. So it's going to be the average of 3 and 6. So that's 9, 4.5. Okay. And then my third quartile is my median of this part of my data. So 31 and 35. So this would be what? 66 divided by 2, 33. So this is my third quartile. So as you can see, my minimum is 2. My first quartile is 4.5. My median is 12. My third quartile is 33. And my max is 56. So I can think of these quartiles as my minimum is at my point at which all my data is below this, right? The first quartile is the point at which 25% of the data, lies below, less than 4.5. So 3 of my data points are less than 4.5, right? But there's a couple of different ways to come up with quartiles. You think about this, 25% of my data is also less than 4, which is also, it's also less than 5. It's also less than 6. So there's a lot of different ways that people handle quantiles, and every program does it a little differently. Your calculator actually does this a little slightly differently than the way I've done it here. It's still valid. It still meets this criteria, and that's the important part. So 25% of the data lies below 4.5. Of course, 50% lie below 12 and above 12. 33% or 75% lies less than 33, and everything lies below, equal to, less than or equal to 56. So we're able to break up the data into 4 pieces, and it kind of gives you an idea of what your data kind of looks like. It's just another way. So these are listed in our one variable stats, not something you're going to have to do by hand. And you can use these to create a box plot. So let's take a look at what this looks like. So here's a good example of a box plot. So this whisker right here, this shows your lowest value or your minimum. This one shows you your lower quartile, Q1. This one is your median, not your mean, be careful. This one's Q3. This one shows the max. Now, sometimes outliers show up like this. Sometimes if we have an outlier, we may put an extra dot out here. This is truly the max observation, and this is the highest observation that is not an outlier. That is occasionally how it's also done. So here's a funny example of that. Girl says, "Can my boyfriend come along?" I'm not your boyfriend. You totally are. I'm casually dating a number of people, but you spend twice as much time with me as anyone else. I'm a clear outlier. So there's the box plot, and here's her. She's the outlier. So it's just kind of funny. So to make box plots on your calculator, so let's talk about this. And we can actually go ahead and do this with the data that we have in there. So we're going to take a look at your calculator again. So what we're going to do, let's do list 1. We'll actually look at both of them. We'll look at list 1 and list 2. Click on second y equals. That brings up your stat plots. So you make sure your first stat plot is turned on. In order to do that, you're going to hit enter. And then enter again to turn it on. Make sure on is highlighted. Then cursor down to type. Under type, use your side cursor until you're on the box plot picture. Either one is fine. This first one will give you outliers as extra dots. This other one will not. It'll put your min and your max just like that. I'm going to go ahead and use the first one. So I hit enter. And don't forget to hit enter after this. And then, oops, move this over here. Okay. So fill in X list is list 1, which is the default, so mine's already there. Frequency 1. And the mark, like I said, it doesn't really make a difference what mark you use. This one's fine. So now we just hit graph. Now sometimes nothing shows up. If nothing happens, hit zoom 9. So we hit zoom number 9. And there it is. So there's my box plot. Now I can look at my box plot, investigate, using the trace key. So I can investigate this using the trace key. If I hit the trace key, it'll give me my minimum, the first quartile, which is 45, the median, 47.5, and I'm just hitting the side key to do this. It gives me the third quartile, and it gives me, now this one does not give me the max data because there is an outlier, and that outlier is 66. That's considering that an outlier. So it actually only gives me 58 here, and it gives me the max out here as an outlier. Now let's go ahead and try, let's redo this, and let's change this to number 2. So second 2, and graph. Oop, let's zoom in, let's change the zoom 9 again. We have everything, and this time look at this. Now the minimum is an outlier. So if I look at this, hit trace, I can see, go back here one, the minimum X is 20, which is an outlier, but the next one's 37. And the median and the first quartile are very close. So what this tells me is that I have skewed data. So let me show you what that looks like on the next slide. Oh, I don't have another slide. Okay. So box plots can tell you what shape your data is also. If you look something like this, this means you're skewed left. If your box plot looks like this, or if you have this here and then there's an outlier out here, this means you're skewed right. And if your box plot looks fairly even, then you're symmetric. So this is left, this is right, and this is symmetric. Okay, I think that's enough. It was almost an hour. I'll see everybody in class. Don't forget to do your quiz.